Okay. Thank you for having me. And tonight I'll cover a bit about the Big Bear Solar Observatory. I will have an introduction page for myself. And what I want to also stress today is the relationship between the Big Bear Solar Observatory and the new 4-meter Daniel K. Inouye Solar Telescope. So let's jump right into it. I've titled this the Goody Solar Telescope, Big Bear Solar Observatory, the highest resolution solar telescope in existence. And that is a title that we got rather used to calling ourselves for the last decade or so. But this is coming into a new era where we have to update the title we give ourselves. Now with the first light of the 4-meter telescope, we have to accept the fact that that title has gone to the National Solar Observatory. And now Big Bear is the second place highest resolution solar telescope. So moving on, a little bit about myself. My name is Claude Plymate. I have done a career in solar astronomy for 36 years. From 1986 till 2011, I was with the National Solar Observatory at the McMath Pierce Solar Telescope. I had numerous positions while there. Leaving as an engineering physicist, I'd worked as the infrared engineer on the facility, site manager, numerous other positions as well. In 2011, I made the jump from Big Bear, from the McMath Pierce telescope to Big Bear. They recruited me as the telescope engineer, chief observer for the new 1.6 meter telescope. And so I spent nearly 10 years under the New Jersey Institute of Technology Big Bear Observatory. However, at the start of this year, January 1st, I retired. I am now on my own and back to being a gentleman amateur astronomer. So starting off, first of all, where is Big Bear Lake? For those of you who have not come up the mountain to Big Bear or been to the Riverside Telescope Makers Conference, we are, excuse me, I'm not used to being retired. I will be slipping throughout tonight and saying we when I should be saying they. I am now retired, but so you'll have to excuse me on that. And also let me say that I'm assuming we're all astronomers here, so I will not shy away from using astronomical jargon. I have a lot to cover tonight, so that will help things move along. However, it's quite possible that I might slip and use something that is more specific to solar astronomy, or for if any reason I use something that you're not familiar with, don't be sure to ask a question, ask me to elaborate. Anyway, you're down, I assume, somewhere here in the Panoma area. And up in the mountains of San Bernardino is Big Bear Lake. Zoom in. Here is Big Bear Lake. If you'd ever gone to the Riverside Telescope Makers Conference, which Teresa was on the board of directors for, that was up in this area. The lake here, zoom a bit more, and out in on the north side, north shore of the lake, extending 1,000 feet into the lake is a causeway with the observatory dome right at the end. I assume you can see my cursor that I can use as a pointer here. Excellent.
Yep.
So why Big Bear Lake? Well, Caltech wanted a world-class observing site for solar astronomy. Yes, they already had Palomar and of course Mount Wilson, which did have solar facilities, obviously, but they thought that they could do better. A big problem with solar astronomy is, of course, as you all know, ground heating causes thermals up around your telescope, which distorts the image and can destroy your scene. Solar astronomy is necessarily done during the day where there is a lot of ground heating, and the hot ground rising up around the telescope will cause problems. So the idea was, well, I wanted to find something better than for daytime astronomy, as opposed to Palomar and Mount Wilson, which are excellent nighttime sites. Of course, SoCal mountains are already known for good, stable astronomical seeing. Again, examples are Mount Wilson, Palomar, Mount Laguna, et cetera, et cetera. But there is the added constraint during the day of that ground heating. Fortunately, here in Southern California, we also enjoy rather good weather statistics. So Caltech wanted to find an ideal site for solar astronomy. And one of their astronomers, Bob Layton, back in the 60s, had the idea that a water surrounding a telescope would suppress that daytime heating and minimize that the thermal and microthermal environment around the telescope, preserving the natural astronomical scene. A site survey of several locations around Southern California, different lakes, etc., were conducted, and Big Bear was selected as nearly the ideal site for a solar observatory. Professor Hal Zurin, a well-known solar astronomer who put out this well-regarded solar textbook back, I think that was early mid-70s that was put out, was really spearheaded and led the development of Big Bear and was named the first director at Big Bear. The first generation telescopes at Big Bear back in 1969, first light, were a pair of twin 10-inch refractor telescopes. Here are some old pictures of that. This is well before my time, so I can't tell you a lot about the facility at that time. But in that single spar were two 10-inch refractors that fed two cameras at the focal plane here. The cameras, detectors of choice at the time, were 16mm film cameras. And I can see that each one was being fed through a narrowband LEO filter. These were Halley filters. I recognize them. Likely one for H alpha, maybe one for calcium K, I'm not sure. And then later another refractor was added up on top. Now, I'm told there was also a 16-inch reflective coronagraph at that time that never worked. So was never really used. And I can't tell you much more about that generation. Fast forward just 3 years, and the next generation telescope was installed at Big Bear. The next telescope was a 26-inch reflecting telescope that was built to fly on Skylab 2. Now, you've never heard of Skylab 2 because Skylab 2 did not survive funding, never flew. And so there was this orphan space telescope. Hal Zurin somehow convinced NASA that they should test the telescope at Big Bear. So it was transferred to Big Bear. The telescope was installed inside of a vacuum chamber. It's in a vacuum chamber to minimize thermals inside the telescope rising up from internal heating. It is a solar telescope after all. And that the entire telescope and vacuum chamber and a couple other refractors that held off of it were put on the same mount that originally carried those two 10-inch telescopes. That was one overburdened mount, I'm sure. The telescope, as we'll say later, was removed from the facility back in 2007 and was given over to the LA Astronomical Society. Here's a picture. A few years ago, I was invited down to give a talk to LA at Griffith Observatory. And the deal was I would come down and do it if they pulled the telescope out for me to see it. And so this was at that time the latest iteration of that 26-inch solar telescope. Had been repurposed as a Newtonian onto an altazimuth mount that they were pulling out for public viewing. I'm told that their plans currently are to reinstall it at their dark side at some point. Now, fast forward to 1997, Hal Zurn retired. At that time, Caltech was investing heavily in nighttime astronomy. They were developing the twin 10-meter Keck telescopes in Hawaii. So the decision was made at that point to just divest of their solar assets, which included the Owens Valley Solar Radio Array out in Eastern California, and BBSO, Big Bear Solar Observatory. A request for proposal was put out and for operation of BBSO. And of all places, New Jersey Institute of Technology wrote the winning proposal. Now that at the time, honestly, before that, I'd never even heard of NGIT. And that seemed a very odd fit to Big Bear. However, as it turns out, several of the faculty at the New Jersey Institute of Technology's Center for Solar Terrestrial Research did their PhD research at Caltech, their PhD work at Caltech, and were very familiar with the BBSO and the potential it really had. So Dr. Phil Goody was the one who really spearheaded and pushed through the proposal for NGIT to take over. That was the winning proposal. So Phil Goody was named first NGIT director at Big Bear. And here's the alphabet soup that the observatory is under. Big Bear Solar Observatory is a field laboratory of the New Jersey Institute of Technology's Center for Solar Terrestrial Research. Now, Phil took over at the end, pretty much, of the 20th century, and right then was a very dynamic period in solar astronomy. Around that time, the Japanese were planning a half-meter solar space telescope called Hinode, which would be launched in 2000. I forget now. And at the same time, my employer at the time, the National Solar Observatory, was starting plans for their 4-meter solar telescope, which has now been rededicated as the Daniel K. Inouye Solar Telescope. So in that environment, Phil faced the question of how could Big Bear continue to be relevant? Well, he knew he had to think big. The real question is, how big could and should he go? Well, in telescopes, as we all know, size matters. The larger the aperture of your telescope, the more collecting surface you have, so the things or objects one can see. That is, of course, not the primary concern for solar astronomy, but aperture also defines resolution. And we're all familiar with that famous equation, the only equation I think I have tonight, of lambda equals 122 times 1.22 times theta equals 1.22 lambda over d, saying that the angle at which you can just resolve is proportional to the wavelength. If you hold your aperture steady and go to longer and longer wavelengths, your resolution degrades. If you go to shorter and shorter wavelengths, you get better and better resolution. On the other hand, if you hold your wavelength constant, larger apertures give you better and better resolution. Now, I've plotted resolution on this graph below in arc seconds as a function of aperture. And not surprising, as you go to ever larger aperture, the angle which you can resolve on the sky gets smaller and smaller. Here at an eighth of a meter, only 5 inches across, you're already able to resolve an arc second, come down to a quarter meter. You're down to a half arc second resolution, half a meter, which is 20 inches. You're down at a quarter arc second. So this is down where Hinode lives here, and on and on. The problem is unfortunately, on the Earth's surface, the atmosphere limits the resolving power that we can achieve in a telescope. And even at the best locations on the Earth's surface, the image quality is limited to maybe a half arc second. So if you're here in the, well, I plotted this assuming the middle of the visible, which I call 500 nanometers. If you come down, here you are at a quarter meter, only 10-inch aperture. And at that point, you are matching the best seeing you can expect to get on the Earth's surface. Larger apertures beyond that, well, you'll get more intensity, but you are really limited by that atmosphere. Yes, there are instances where that can be occasionally beaten by lucky imaging, things like that. But in general, this rule of thumb holds that no matter where you are on your surface, you are limited by that your local seeing. And to paraphrase Jodie Foster, anything above 10 inches aperture is just wasted aperture. So, okay, space, of course, has perfect seeing above. Oops, okay, here we are again. Above the distorting effects of our atmosphere, space telescopes have effectively perfect seeing, but is exceedingly expensive. My rule of thumb is about 3 orders of magnitude more expensive. So take your $1 million telescope. If you want to turn that into a space telescope, I figure you're talking at least $1 billion at that point. That is, of course, completely prohibitively expensive. So what to do? The answer comes in the form of adaptive optics. And by the way, if you have questions, feel free to interrupt me at any time. I'm happy to take questions, and if so, I can blame you for going over time and not my horrible time management. So anyway, adaptive optics. This was originally conceived of in the 1950s up at Mount Wilson, I think by Babcock. But try as they might with the technology of the time, it was completely impractical before the advent of high-speed digital computers. However, in the late 70s and through the 80s, in secret, the idea continued to be developed by the Department of Defense, and finally, at least partially declassified in the late 1980s. So from then on, astronomers have embraced the technology and developed it dramatically. I hate to just nutshell such a fascinating topic, but in the interest of time, we're going to have to move along. I can't say much. If you'd like to find out more about adaptive optics, that's a talk I I love to give, so invite me back sometime. Anyway, in essence, above the atmosphere, you have essentially a perfect plane wave that coming through our atmosphere will get distorted. Somewhere in the telescope optical train, you'll have a deformable mirror that can, under computer control, be distorted to any arbitrary shape. The computer commands it to take on just the correct shape to compensate that wavefront distortion that it is measuring, reflattening the wavefront, and sending that corrected wavefront onto the science cameras, and thus restoring the diffraction limit of the telescope onto the science camera. The downside is those corrections have to be computed, calculated, and fed back to that deformable mirror faster than the sky has a chance to change. So that has to be done at least in the kilohertz range, certainly faster than, say, 1,000 times per second. At Big Bear, the AO system, the adaptive optical system there works at between 1800, 1.8 kilohertz, and can occasionally make it up to 2 kilohertz. So in that range. And yes, an adaptive optics system that is properly functioning, properly designed, can reconstruct the diffraction limit of a telescope, i.e. as good as a space telescope. But the dirty secret is that it only applies over a very narrow field of view. Think about the fact that you are correcting for a wavefront distortion that's coming from one point on the sky. The wavefront distortion coming from another point on the sky will be different, and that correction will no longer apply. So what you find is the correction you get from an adaptive optics system can be very small, maybe only a few arc seconds across, and then it slowly degrades out to as if you didn't have an AO system after that. Now, typically a deformable mirror is a small, thin piece of glass somewhere in the optical train with that can be distorted very, very quickly. Obviously, you cannot distort the primary mirror very quickly due to the inertia of all that mass. So a small mirror is typically used. This is the mirror used at Big Bear. It's only 100 millimeters across with 357 piezo actuators on the back of it, and a bundle of wires down here that's the electrical connections to each of those piezo controllers on the back surface of that roughly 1 millimeter thick, 100 millimeter diameter mirror. And unfortunately, that's about all the time I have to talk about adaptive optics, except to give an example. Now, I hope my video is coming across somewhat smoothly. I hope it's not too choppy. Here's an example of natural seeing at Big Bear. This is actually a pretty bad observing day.
Yes,
here's
we can see that.
A video taken a fairly bad seeing day. This is 40 arc seconds across with natural seeing. Turn on adaptive optics, and that is what you get. A dramatic improvement. You can see down to, you can see there are small bright points that are well sub-arc second in there. But of course, we're not done yet. Each frame in this movie is actually 100 frames deep. And in post-processing, a technique known as speckle reconstruction can take those 100 frames and pull out the highest resolving element at every point across the frame. And so in post-processing, this is, oh, I should get my cursor out of there. This is the type of image you get, which again, I hope this video is coming across relatively smoothly. It is awesome. I can stare at this for hours at a time. Now, keep in mind, these granules are maybe 2-ish arc seconds across. The dark intergranular region is well sub-arc second. These magnetic breakpoints also well sub-arc seconds. So yes, we are fraction limited in this movie. Going on. So again, how big is big enough? Well, theory suggests that there has to be a minimum spatial scale on the sun. Keep in mind, the sun doesn't have a solid surface. Photons are being emitted over a range. There's scattering, etc. So the smallest structure is going to be something on the order of a half 50-ish kilometers, which would be 0.07 arc seconds, which to hit that, you need at least a 1.5 meter aperture telescope for the visible spectrum. Now, I kind of like the way NSO stated this on their DKIST page, so I copied that here. The main driver for a large aperture is the need to spatially resolve the fundamental length scales in the solar atmosphere, the photon mean free path and the pressure scale height, meaning, well, photons are being emitted from several different heights and scattering, etc. To resolve both the fundamental scales, a resolution of, they're saying, 70 kilometers or 0.1 arc seconds is required in the photosphere. Okay, I said 50, they say 70, so we're in the ballpark. In addition, simulations suggest that some magnetic structures might be as small as 35 kilometers. So yeah, okay, we're in that ballpark, 50 somewhere kilometers, something like that. So yeah, you need at least a 1.5 meter telescope. Plus, Big Bear was somewhat partially justified and designed as a technology demonstrator or pathfinder to the NSO's 4 meter Daniel K. Inouye telescope, which has now achieved first light as of December 12th, 2019. And here is a picture of the dome up on Haleakala in Maui in Hawaii. The big dome is, of course, DKIST. Now, the BBSO 1.6 meter solar telescope, the 26-inch, that telescope did not fly on Skylab 2, was a real workhorse telescope. It was in operation from 1972 and wasn't removed until 2007. So it had a 35-year run. That's quite good. It was removed in 2007, and just months later, they were able to achieve first light on what was then called the new solar telescope, the 1.6, in May of 2008. Well, Phil Goody eventually retired in 2013. The current director, Professor Wenda Chow, had a ceremony. We rededicated the telescope in Phil's honor in 2017 as the Goody Solar Telescope. Here's the plaque that's now adhered to the side of the telescope pedestal. Goody Solar Telescope, named in honor of Phil R. Goody, BBSO director, 1997 through 2013, and distinguished professor, July 2017. So let's take a little tour of Big Bear. Now, again, come drive up to Big Bear Lake. The north side of Big Bear Lake is Highway 38. A spur off of Highway 38 is called North Shore Lane. Stop right here, and to your north will be the main onshore campus facilities. To the south is the 1,000-foot causeway leading up to the dome. Again, look north, and you'll look into a parking lot that, and you'll see the main facility building in front of you. Off to the right here is a director's residence. To the left, admin building, where the admin assistant, Erica Noro, resides. A machine shop here. Behind this building is another building, long building with 13 offices, 5 dorm rooms, a meeting hall, kitchen, and over on the left, a garage. Not shown in this picture off to the right is a metal building, officially known as the Hartley Solar Lab, unofficially often referred to as just the barn. And then directly to the right is another residence called the Mud Cottage, where one of the scientific programmers, Sergei Shumko, and his wife Alla currently reside. Turn around to the south on the other side of the road and you face down that 1,000-foot causeway. Moving down the causeway to about this level, we'll stop and look off to our right, where you see this, this storage container. This is one of 6 identical telescopes built by the National Solar Observatory, part of the GONG program. GONG stands for Global Oscillation Network Group. It is a network of small telescopes placed around the world that monitor the sun continuously. Well, they get about 95% coverage due to weather. There's a small input window here with this turret here that reflects light down to the instrument inside, which has a couple of instruments. One is a helioseismology experiment that looks at oscillations trapped inside the solar surface, looking at how those refract through the interior of the sun. They're able to actually model the interior of the sun and determine many things like magnetic fields, magnetograms. And there's also a narrowband H alpha filter in there that gives real-time H alpha full disk images. Just Wednesday, 2 days ago, I caught wind of a press release, caught several of us off guard, that the NSO put out that they are giving over operation and management of the GONG data products to the NOAA Space Weather Prediction Center. So now, since NOAA uses those data products for their space weather predictions, they are taking over management of the data products. My understanding is that NSO will continue to support the telescope and the structure, but they are managing the data reduction and distribution. And you can find that, that press release down here at nso.edu/press release. Now, continuing down the causeway, we next come to this small dome here on the right, which is officially called the Hartley Earthshine Dome for historical reasons. It currently houses just a single telescope that is a 100mm refractor F15 that feeds a high-speed CCD camera through an exquisitely narrow H alpha filter. It was a Leo filter built by Zeiss back in the 60s using optical quality calcite that just can't be found anymore. It, for many, many years, was part of an H alpha global network, but that isn't used for science much anymore. Mostly the product coming off of it now is used for the operator in the main telescope to get a real-time view of the sun, looking for targets of interest, flares erupting, things like that, or erupting filaments, whatever. So here's an example of an H alpha full disk image taken from the telescope, which right now it takes an image every 30 seconds and reports that off. Finally, we come to the Goody Solar Telescope itself, the GST. We will enter through these doors here. There is a small patio we'll pass through that just has a compressor and a transformer, etc. Then come to the first floor facilities, which we came in through this door here. Off to our left is a bathroom. To the right is a janitor's closet. There is a guest observer's office on the left, and what used to be my office on the right. I'm not sure how they've remixed that since I left a few months ago. I should actually ask about that, see what's in my office now. Then in the center, there is an electronics lab. What we'll do is we'll just turn around, go through this door, which, oops, jump the gun there, which takes us into a stairwell, up a couple flights of stairs to another door. We pass through this door. Now, right in front of us will be the Coude lab. Off to the left is a bathroom, which I'm not going to show you inside the bathroom. Off to the right is the main observing room. So let's turn to the right and go into that main observing room. Here we are. Now we just came through this door. The window here looks out over to the north along that 1,000-foot causeway. This is Nicholas Grosset, who is the optical engineer for the facility. And that day I took these pictures was the operator. You can see it's fairly recent. We were all masked, etc. There are numerous monitors and consoles in the observing room. Down here, these monitors are mostly used for science camera operation. These monitors here are telescope operation monitors. And on this screen here, there's also control of the small dome, and that is that H-alpha image coming off of the small telescope I was talking about. Down on the left side of the bench here is mostly adaptive optics control. Above is a console that reflects what Gong is doing, and then more monitors up on the wall that are just general purpose information. Now, if we turn around and look through the doorway directly behind us, we'll be looking into the electronics and computer room. In here is the electronics racks for the computer, adaptive optics, some of the camera instrument control computers, archive data computers and data reduction computers. And this rat nest up at the top is the Ethernet IT. So turning around once again, we're going to go back out the door of the observing room. And instead of turning to our left to go down the stairwell, we're going to turn right and go into the Coude lab. Now, the Coude lab, or instrument optics lab, is where most of the instruments for the telescope really are. And it's very crowded in there, difficult to get a representative image. It's keep in mind this facility was built for two 10-inch telescopes, and now a 1.6 meter state-of-the-art telescope is sandwiched in there. You can imagine space is a premium. So in the Coude lab, there are optical benches pretty much everywhere we can fit them, to the point where benches are actually stacked too deep. There is a bench mounted vertically on the telescope pier, which includes adaptive optics on the vertical pier, a high-speed CCD, more for optics. Down on the lower bench is most of the visible and near infrared instrumentation. These sort of cylindrical things are Fabry-Perot interferometers, which are conceptually very similar to Etalons, like you would find from a Daystar filter, except for the fact that instead of being tuned by temperature and expansion, they are tuned by by piezoelectrics. So it can be varied in wavelength very, very quickly. And I'm talking on the order of milliseconds, and are exceedingly narrow band. This one is used for H-alpha. These two stacked ones are used for the near infrared. And down here is the near infrared detector, the cryostat for that detector. Now we're going to go back out of the Coude lab. Sorry, I'm moving along quickly. But again, lots of cover tonight. We go up yet another flight of stairs. We come to the third floor. This was originally the observing telescope floor for the facility. However, the new telescope needed to be raised up a bit, so the pier was re-engineered, strengthened dramatically, and raised up a bit. And so this floor was able to be repurposed as another coude lab or instrument lab for the thermal infrared. This large instrument here, which looks kind of like a big gold Liberace piano, is really a large cryostat where there is an all cryogenic spectropolarimeter, very high resolution cryogenic spectrograph that works out in the infrared between 1 and 5 microns. For those who aren't familiar with, if the middle of the visible is 0.5 microns, 5 microns would be 10 times that wavelength. So that's the range that works over. So it is a high resolution spectrograph that works in that range, but it also is able to do polarization to characterize magnetic fields in the solar atmosphere. If we come around the backside, there's a very complex 4-optics system for it. Just in front of the input window, there is a rotator here that carries the polarization optics. Up on a bench up here, since it is a story above where the adaptive optics is, this instrument is unfortunately not fed by adaptive optics, at least not yet. Instead, this bench is just a what I would call an image stabilizer or a fast mirror that just takes out image motion. There is also a beam scanner here that while we hold the image steady, it can it can translate the image across the input slit of the spectrograph. So now, last flight of stairs, take a breath and walk up one more flight, and you finally actually arrive on the dome floor. And here is that 1.6 meter Goody solar telescope. And here's that dedication plaque dedicating it as the Goody solar telescope. Now let's shift gears just a little bit, take a bit of a breath, and let's talk a bit about the different components in the telescope. First of all, the primary emitter. Well, back when all the project started, the University of Arizona was in the process of developing the Giant Magellan Telescope, that truly monstrous telescope going down in Chile at La Silla Observatory. No, Los Campanas. Yeah, Los Campanas, I think. The Smithsonian Observatory down, excuse me, the Carnegie Observatory down there. And so they needed to demonstrate the ability that they could grind the mirrors for this telescope. Keep in mind that this mirror, this telescope, is made of, will be made of 7 8.4 meter mirrors that are all ground to replicate the shape of a single 25-ish meter parabola. So while the mirror in the center is a symmetric mirror, a conventional parabola, these mirrors around the periphery, these 6 mirrors arranged in this flower petal arrangement, are segments, off-axis segments of a parabola. Nobody had ever produced such a large, so off-axis mirror for astronomy previously, and the Mirror Lab needed to demonstrate that that could be done. So Phil Goody cut a deal with the University of Arizona that BBSO and the U of A would split the costs on the development of that mirror. I think there was also some Air Force money in that. At the end, the University of Arizona got to develop a demonstrator sub-sized mirror and figure out how to use their computerized maps and how to figure that mirror. And surprisingly importantly and difficult was how to test that mirror. And in the end, BBSO got the mirror. So the primary mirror, that 1.6 meter primary, which is actually a 1.7 meter full aperture mirror, is a 1/5 scale model of a GMT mirror. So that is where the mirror came from. The primary mirror is a daughter segment of a 5.3 meter imaginary parabola. It doesn't really exist, but I always talk about how imagine a segment cookie cuttered out. That isn't physically how it's done, but that is how to imagine the curvature of that. So a 5.3 meter diameter parabola, that's 17.4 feet across. It's made of ultra low expansion Zerder, a shot product. The substrate, and it's only 100 millimeters thick, although 63 inches across, producing an all reflected, unobstructed telescope system. Now, for solar, we prefer unobstructed optical systems to avoid diffraction. You know, whenever you have a spider or any structure in the beam, you'll get diffraction features. Well, that's not a problem for stellar images. I mean, first of all, they're kind of pretty to see stars as little crosses, and it's really easy to do photometry or astrometry, saying, well, the star is right in the middle of that cross. But on an extended object like the sun, every resolving element across that image will have diffraction spikes, which will add together to make a cloudy decrease in the contrast. So to maximize the contrast and the resolution, a all reflective, unobstructed system is preferred. Also, being all reflective allows observations in both the visible and infrared spectrums. Now, a lot of astronomers will be surprised to find out that in a solar, we tend to prefer Gregorian optical systems as opposed to a classical Cassegrain or something like a Ritchie-Chrétien, something like that. And there is a good reason for that. Here's a diagram of your classical Cassegrain telescope with the parabola at the back, which is making a converging beam down to a focus that would occur here. But ahead of that focus is a convex hyperbolic curved secondary. That convex system then sends a slow F ratio beam back to the focus, which is behind the primary mirror. Switch that to a Gregorian, and again, you have that same parabolic mirror, but this time, instead of a convex mirror ahead of the focus, there is a concave elliptical mirror behind the focus. Now, again, a lot of astronomers feel that the Gregorian telescope is an inferior optical design to a Cassegrain, that it has more off-axis aberrations than a Cassegrain. Well, keep in mind, on a large solar telescope, you are not a wide field telescope. Due to energy constraints, you are by definition a fairly narrow field telescope. So that's really not a concern. What is very important, however, is a Gregorian gives us access to that first primary image. Now, the 1.6 meter diameter mirror has a collecting surface, if you do the math, of about 2 square meters surface. Now, I don't know, you might have heard of the solar constant. The sun is constantly irradiating the sun, with about 1.36 kilowatts per square meter of energy. Well, there's a lot of reflection and scatter in the atmosphere, but I figure something of the order of a kilowatt per square meter still makes it to the Earth's surface. So that 2 square meters of mirror surface is collecting up and concentrating 2 kilowatts of power into a 36 millimeter diameter image. That's 2 kilowatts inside a 1.4-inch circle. That's enough energy to melt and even vaporize metal. Here's another optical diagram showing, again, that unobstructed reflective optical system. The beam comes in, reflects off to the side. Now here is the important point. Here is the primary image of the primary mirror, the first image, which is ahead of that off-axis elliptical secondary mirror. So we have access to that primary image, that first image, without interrupting the beam, either coming or going. So in that first image, right here, here's that off-axis elliptical mirror. And while I said the primary mirror is not actually cookie cuttered out of a parent parabola, the number 2 mirror actually is cookie cuttered out of a single optic, giving a single elliptical optic. So that gives the observatory actually 2 number 2 mirrors. So one can be out of the telescope and being cleaned or reilluminized or silvered or whatever, while the other is in service. And at least I assume still, and at the time I left at the beginning of the year, this was actually the backup number 2 mirror. Well, just ahead of that number 2 mirror is the primary focus. The telescope forms its primary image, an image of the sun, on this highly reflective aluminum surface here. This is called the heat stop or heat dump. It is a polished aluminum surface that is constantly cooled by water on the back to keep it from melting down. So almost all of that 2 kilowatts of power are reflected away and scattered off the side of the dome. Some small amount is absorbed into the substrate and carried away by that chill water that's constantly circulating through. But right in the center of that is a 3 arc minute, 3.6 millimeter across aperture that sends about 1/10 of the solar diameter on down to the secondary mirror and the rest of the optical train and instruments down train. Now, it is imperative that the telescope controls where that primary image hits. Again, if it hits something that is not cooled and highly reflective, that I won't say could cause, it will cause severe damage. So around the periphery of this heat stop are a array of heat sensors, temperature sensors. If any of them sees an anomalous reading outside some range, I forget what it was set at last time I was up there, it will open a solenoid down here. This cart will be pulled along these 2 tracks upward with this spring, sliding this highly reflective stainless steel plate into the beam, and we'll try to protect the rest of the structure from that beam. That actually happened once before I was hired at the telescope. I'm told it was exposed to the beam for about 30 seconds, and there is a hole burned through that stainless steel plate. On the left, to help keep track of where the solar beam is, there is a web camera mounted on the side of the telescope, looking through a cheap solar filter, like the same material you get in solar eclipse glasses. Bought it from, I think, Rainbow Optics, and put it on the front of that web camera. Here's a frame grab from that shows the solar disk and that 3.6 millimeter 3 arc minute aperture right in the center. So at this case, the image can go anywhere in this area, but at the moment the telescope happened to be looking at right at the center of the disk. Now keep in mind that since this aperture is about a tenth the aperture, the tenth the diameter of the solar image, it passes only about 100th square law of the beam, so that 2 kilowatts is reduced down to about 20 watts of power onto the secondary and on down to the instruments downstream. That can be handled. Keep in mind, we are not that within that 3 arc minute image that there is still the full brightness, the full intensity, and the full resolution the telescope can deliver just over a small field of view. Moving on. Now to shoehorn the new 1.6 meter telescope into the existing facility, the original 30-foot hemispherical dome had to be replaced with a 34-foot diameter 5/8 sphere, which actually is a modified radar dome. To fit in there, the telescope had to be raised up a bit to match the maximum diameter of this bulging out, which kind of looks like a Jiffy Pop here, dome. The mount itself was designed and built by DFM Engineering up in Longmont, Colorado. It is a heavily modified version of their standard 50-inch telescope mount. So here's an engineering drawing of the telescope. Here's an actual photograph of one of their standard telescopes. So you can actually see at least the pedestal and RA drive, or in solar terms, HA drive, is standard, but the upper part of the telescope had to be modified heavily to be the off-axis optical system that is used at this facility. The facility uses 2 CUDE instrument labs, one floor down for the thermal infrared, the SIRA instrument. 2 floors down are most of the other instruments, both visible, near infrared, and adaptive optics. There is a instrument slide on a track at the south end of the polar axle there that you switch between optics to feed one bench at the 1 story down, or switch over to the other to go through a port here down to the main CUDE lab 2 stories down. Now that number 2 mirror, the secondary mirror, is mounted on a hexapod. The structure of the telescope does not have a standard truss mount like you expect on a standard symmetrical telescope. It has kind of an A-frame off on one side of the telescope. Unfortunately, that design does have flexure. And it's unfortunate, but can be lived with. There's a discontinuity around the meridian where suddenly it jumps by about 20 arc seconds. But it's been learned to prepare for that and to compensate for it. But also there are other flexures through the day. And also, of course, some thermal expansion as the mirror warms, etc. So to compensate for that, the secondary mirror is mounted on a hexapod. These are 6 struts that can extend or contract through computer control to try to minimize the misalignment, focus, aberrations. That is done manually by the operator throughout the day. We can see the aberrations build up by the parameters showing up on the adaptive optics screen and try to tune that out by the 6 degrees of freedom. It's 6 frets, so the 6 axes will give, let's see, up, down, left, right, in, out, rotation, tip, and tilt. Yeah, that's 6 axes there. So that's the primary mirror cell is a 36-point passive flotation cell. It was originally designed for active optics. All this array of holes on the back of the mirror cell were initially meant to hold actuators, little electric motors that would back up the passive system to push and pull on the primary mirror to keep it in shape. In practice, it was found that the passive system works well enough, so the active optics were never installed. The passive system is an ingenious design that goes all the way back to Mount Wilson. There are 36 the levers with little 5-pound weights on them, factor of 10 force multipliers that are adjusted to apply just the right amount of weight to the mirror to just support it. You know, you can imagine that's not too difficult to do. Pointing at the zenith, you can adjust those counterweights to just float the mirror at 36 points. The brilliant part comes about is, well, of course, a telescope has to tip to arbitrary points on the sky. Well, these counterweights, since the force vector from gravity is changing, the same vector is changing on each counterweight, causing the counterweights to automatically adjust how much force is applied to the mirror, to automatically compensate for the angle at which it's going, that is pointing. Brilliant. Each one, the 5 pounds, is if it's all the way out, is a times 10 force multiplier. The mirror weighs about 1,400 pounds, so 5 pounds times 10 times 36. If it were adjusted all the way out, would be able to push with a force of 1,800 pounds at the zenith. But they're scooted in a bit where it just floats the mirror and is found to work surprisingly well, to the point where that active mirror cell network was elected never to be put in. This works well enough. Now, keep in mind, this is a solar telescope, not a stellar telescope. A solar telescope does not need to point arbitrarily anywhere in the celestial sphere. It only needs to be able to point between where the sun is, between plus 22.5 degrees declination in the summer to minus 23.5 degrees in the winter. So it only needs to be able to move in declination over a fairly limited range. And at the same time, remember, this is this off-axis optical system. The mirror is canted heavily over to this side. The beam comes way over to the side to the number 2 mirror here, comes down parallel to the side of the telescope, hits a tertiary mirror right here, which sends the beam through the declination bearing off to a 4th mirror and down through the polar axle here, and on down to the Day lab. Since the beam goes through the polar axle, and as the polar axle rotates, the beam is stationary through the day. It does rotate, but it is stationary. The downside of this design is that, well, normally you would think of a typical fork mount telescope. The forks would come up to a declination bearing that would be centered in the center of mass of the telescope. So it'd be a nice balanced system. To accommodate the off-axis optical system, the declination bearing is way down here, well below the center of mass of the telescope. So this telescope is heavily out of balance. Well, you say no big deal. You can just put some really big counterweights down here off of long tangent arms. Well, unfortunately, since the telescope had to be put into a pre-existing building, and I mentioned that this building was designed around a couple of 10-inch telescopes. Um, the telescope is already pushing the weight limits of the re-engineered pier and this building. So counterweights were not an option. And plus, there really just isn't room to put in telescopes off of long tangent arms. So another solution had to be devised. And DFM came up with a solution, I think borrowed from radio telescopes, where there over on this side of the telescope, there is a simple screw jack that can just push up or down to move the telescope up and down in declination. Now, again, being a solar telescope, it only needs to move over a limited range. So that gives enough range of movement. However, that is a tremendous amount of weight that would have to be moved due to this off-axis, out of balance nature of this telescope. So on both sides of the telescope, there are two more screw jacks that push against springs inside these housings. Now, we can calculate how much force is necessary to support the telescope. We know the spring constant on those springs, so we know how much that spring needs to be compressed to support the telescope. And using linear encoders on the back of those housings there, the amount of compression on the spring can be measured, so the computer can keep track of just supplying enough force to the both of those springs to just support the telescope structure. So as I've always said, instead of being a balanced telescope, this one rides on spring shocks. Lastly, there are two tusks that extend, these two tubes along the side of the telescope. Many of you have probably seen things like this at Mount Wilson and other observatories. These are counterweights for balancing the telescope. It is balanced in the lateral direction. However, a bit unusually, the counterweights need to move up or down as the telescope moves in declination. So when the telescope is slewing in declination, you'll hear large torque motors at the fronts of these tubes kick in, moving up and down these two 600-pound weights. Fortunately, the sun doesn't move much in declination through the day, so those two counterweights are pretty much stationary throughout the day and not disturbing their viewing. Now we come to what I call the proof of the pudding running on. I better get moving on this. Proof of the pudding image here. On the right is an early image from at that time, the new solar telescope, NST, the 1.6 meter telescope. On the left was one of the very early simultaneous observations taken from that Hinode half-meter solar space telescope. Same region, same region of the sky, same region on the sun, etc. And of course, you can see there is a true one-to-one correspondence to every part of the image. However, clearly, this demonstrated that the telescope was performing and outperforming any current earthbound or spacebound solar telescope of the time, and that it is able to achieve. Right. Is there a question? I'm sorry, was there a question? I didn't catch that. I guess not. Okay. So let's fast forward a decade, and on December 12th of 2019, the 4-meter Daniel K. Inouye telescope took its first light image, and they released their image. So here is, again, that first very early image from Big Bear in comparison to their first light image. Now, at first, you might be somewhat surprised that we don't get the kind go back, get this kind of improvement. Here we are about 3 times the aperture of Hinode, and you get a dramatic improvement in image quality. Move up again another factor of 2.5 in aperture, and you may be surprised that there isn't that dramatic of an improvement again. But keep in mind what I said originally is there is a limited spatial structure on the solar surface. And it's very likely that the Big Bear telescope should be already approaching that limit. So you can't really expect in the visible spectrum that a telescope even 2.5 times the aperture to get much higher resolving power than we already see. And if you look at it closely, maybe there are some small structures in there. It's questionable whether those are real or some of those are artifacts. This was a first light image. So let's move along and do a side-by-side comparison of the two telescopes. Well, I think you'll see at this point why occasionally Big Bear has been referred to as a baby DKIST. So over here on the GST, it is a 1.6 meter f2.4 off-axis Gregorian telescope. DKIST is a 4 meter f2 off-axis Gregorian. Optical diagrams conceptually very similar, just 2.5 times the aperture. Big Bear is an equatorial telescope, equatorial mount, which simplifies several features, particularly polarization calibration. DKIST, on the other hand, is an altazimuth mount. Well, it is. Come on, guys. Sorry, my cats are misbehaving over there. It is an altazimuth, which is a lighter and a more compact system for them. Now we get to resolution. At the middle of the visible, 0.5 micron or 500 nanometers. Big Bear can resolve down to 57 kilometers. Stop it, you guys. DKIST, same wavelength, can get down to 23 kilometers. Whether there is actually structure there to see is, we'll find out, but debatable. The real point comes when you get out to the astrophysically important lines at 1.5 microns, 1500 nanometers. The resolution of Big Bear is degraded down to 171 kilometers, and DKIST is still able to resolve 68 kilometers, almost comparable to what can be done in the visible at Big Bear. This, I think, really shows the power of potential collaborations between the two facilities into the future. Well, Big Bear could be resolving down to the possible limit of structure on the solar surface in the visible. DKIST could be getting comparable results out in the infrared simultaneously. Go out to the interesting region at 5 microns, and well, the resolution is way down to 570 kilometers at Big Bear and 228 kilometers at DKIST. First light, Big Bear, 2008. First light, DKIST, 11 years later, December 2019. That heat stop for Big Bear has a 3 arc-minute field of view. It is reflecting about 2 kilowatts of power, where DKIST has a 5 arc-minute, so it's a larger field of view, heat stop that has to reject around 13 kilowatts. That is mind-bending. Where Big Bear has a fixed Coude lab with a field rotation, normally taken out in software, at a fixed 15 degrees per hour, the diurnal rate. DKIST has a variable speed rotating Coude lab, with a very expensive option there. Big Bear has a nice suite of visible and infrared imaging, spectropolarimetry instruments. as well as multi-conjugate adaptive optics. At DKIST, their first generation instrument suite is modeled heavily on Big Bear's instruments. So as I said, Big Bear was a Pathfinder technology demonstrator. So their first generation instruments are very similar in concept. The altitude of Big Bear, well, it's 2,060 meters. That's only 6,760 feet at the telescope, which is too low to be a coronal telescope. There's just too much atmosphere above the facility, too much water vapor. It is not able to take observations of the corona, even out in the infrared. DKIST is up 1,000 meters higher at over 10,000 feet. So it is expected that it will be a coronal site in the infrared. Development for the GST, $25 million over 5 years. A bargain, in my opinion, and exceedingly fast. Development of DKIST, about 344 million admitted to over 20 years. That may sound like a huge price tag, but if you go with the old rule of thumb that the cost of telescopes goes as the cube of the aperture, that's right in there. Operations, Big Bear, about $1 million a year. Operations for DKIST, obviously significantly more, $18 million per year on top of a mountain out in the middle of the Pacific Ocean. Unfortunately, COVID-19 has caused significant delays on DKIST. After its first light image in December 2019, it had been expected to then this last fall go into first season science observations. Unfortunately, pretty much we're going to have to just make a do-over on this past year. And it's now hoped that beginning of regular science operations are now expected to be in the fall of 2021, basically a full year delay on that. A couple of other telescopes of note, Gregor, there is a 1.5 meter on-axis symmetric telescope, Gregorian. That's out in the Canary Islands, Tenerife, at an altitude of 2,390 meters. So slightly less aperture, but slightly higher altitude than Big Bear, 7,800 feet. It does have a high order adaptive optics system. It's operated by the Kiepenheuer Institute for Sonnenphysik. Excuse my obliteration of German. Being an on-axis telescope is conceptually a simpler mount and probably more rigid than Big Bear. Probably doesn't have the flexure problems of Big Bear, but it will always have diffraction from the central obstruction, the number 2 mirror, and the heat stop here, as well as the support structures, the spider network. So even though it's only trivially smaller than Big Bear, but it will never really be able to get the same kind of images quite as Big Bear because of the obstructions in there. It had first light in 2012, but had numerous problems. But a year ago, underwent some significant optical, mechanical, and electronic upgrades to achieve the best quality images. And here's the image they released. So it looks like they are now doing quite well and very comparable to what Big Bear is able to do. Keep in mind, this is a very early image from Big Bear with a very early adaptive optics system and data reduction system. So yeah, that can be cleaned up a bit more today. So very comparable then. Next is the Chinese Large Solar Telescope. This is a 1.8 meter, another on-axis Gregorian that appears to be heavily modeled on Gregor. It is being developed by the Chinese Academy of Sciences, their Institute for Optics and Electronics in can do. It achieved first light apparently, and also in December 2019. Very little information is available about it. And one of the press releases did include this really awful image from it, which seems to indicate that it must have some kind of adaptive optics attached, but that's about all I can tell you about it because they're not saying much about it. But apparently, this is currently the second largest solar telescope in existence. However, from the appearance of that image, they have a lot of work to do before it can really live up to its potential. Now, as I said, adaptive optics works very well and can achieve the diffraction limit of the telescope, but over a very limited field of view. There is a new program underway, a joint project between BBSO and the National Solar Observatory to do what's now called multi-conjugate adaptive optics. The first test bed is at Big Bear, and what MCAO does is it utilizes multiple deformable mirrors, not just a single one, as in what's now called classic adaptive optics, but it uses multiple adaptive optics, correcting for different layers in the Earth's atmosphere. That the result is not a better correction. Can start that video again? Come on. There we go. Not a improved correction, which here, but that correction applies over a wider field of view. So that's now we have gone from about a 5 arc-second correction in classic adaptive optics to it's more like a 30 arc-second corrected field in the multi-conjugate adaptive optics. Again, play that one more time. Go. There we go. So small corrected field at that point, switch on multiple deformable mirrors, and you get the correction all the way out here. You can still see that the correction falls off past some point. Now, here's another panorama inside the Coudet lab. In this lower bench here is most of the several of the visible and near-infrared instruments. The entire upper tier optical benches are all taken up with that multi-conjugate adaptive optics development system. Now that early image I showed, comparing to others, this is that same, a sequence made from that same observing day. And this demonstrates the fact that, of course, not only could the Big Bear telescope achieve diffraction limited images, but diffraction limited images over a large extended period in the observing day. And of course, the telescope doesn't just observe the photosphere. It also can look at lines in the chromosphere. Here's a very nice H-alpha line center image showing an active region. And here is what I hope that this is coming across fairly smoothly on your screen, because this, as far as I know, is by far the highest resolution H-alpha video ever made. This was taken October 4th, 2017, and it's just a spectacular sequence. I begged the principal investigator to be able to show this video. And you can spend literally hours staring at this and constantly see something new. Along with line center, since again, these are fabric rows controlled by piezoelectric actuators, as opposed to, say, temperature tune, the line center of that filter can be changed very, very quickly, and it's extremely narrow band. So very quickly, one can scan through a feature like the H alpha line. So when here we are scanning through, when you're in the center of the H alpha line, it is at the most opaque part of the H alpha. So you're seeing high up in the chromosphere. Once you start going off the line center, you're seeing further down into the chromosphere and all the way down to the photosphere. However, plasma that is flowing up in the chromosphere will be either red shifted if it's falling down towards the solar surface, or blue shifted if it's moving upward. So you can map out the velocities of those spicules and those plasma flows. Here we are on the blue side, so you're seeing material flowing upward, going through the line center. Then here we are going off to the red wing, where you're seeing material falling back in towards the solar surface. So you can take that and make movies actually showing, here is a red wing of the H alpha line, showing that plasma infalling towards this the sunspot. Here's an image I'm kind of proud of. I took an active region. I took a blue wing, colored it blue, red wing, colored it red, and center colored yellow. Combine those. Keep in mind these are being held stably by the adaptive optics system, and so long as you can do that quickly enough before it has a chance to change, so a few seconds between these different wavelengths, you can actually make a Dopplergram out of that. So here is an image showing the velocity flows in and around that sunspot. Red is material falling down, blue material falling up, yellow is kind of stationary. And I thought it just made a spectacularly pretty image. So I'm very pleased to get to share that with people. I'm really getting on in time, so I'll just say that we can also use polarization out in the infrared to map magnetic fields in the solar atmosphere. I won't go into exactly how that is done, except to say that as you go to longer wavelengths, you are more and more sensitive to weak fields. So here we are at 1.5 microns. Here is the intensity, just showing what the surface looks like, and then different polarizations, being able to, from that, tease out the magnetic field orientation, strength, polarity, and even inclination. I wish I had time to say more about it. That same instrument can look at another line out in just beyond the visible at 10^30 angstroms, just beyond a micron. This is a helium line formed kind of like H alpha, but instead of in the chromosphere, this is formed at the very top of the chromosphere, really in the transition region up near the corona, and is much more optically thin, so you can see through it down to the photosphere. But being that it is thin like that, the structure you do see trace out the magnetic field lines very, very nicely. And in this really nice sequence, you can see how a very complex magnetic field orientation undergoes a flare, and is how there's that flare, and you get this beautiful, simple arcade orientation in the post-flare era. So really a nice sequence there. Let's see that one more time. There you go. And then that arcade that forms in the post-flare period. Now, back to the photosphere. Here's a really nice sequence taken of a large sunspot with a well-formed light bridge. You can see, again, this is one of those that you can spend a very long time staring at. This was taken in 2015, back when we used to have sunspots. Well, the sun is starting to wake up again. But here you can see bright points down in the solar umbra, see their motion. Those are subarc second features. You can see very clearly that the light bridge, what that is, that's convection working its way up through the umbra. You can see the flow velocities in the penumbra, etc. A spectacular series. And I just hope that this is translating somewhat well in this Zoom meeting. I fear that this is getting probably jumpy on your side and doesn't look nearly as nice as what I see on my screen. Then November 11th, 2019, there was the transit of Mercury. We were able to lock the adaptive optics onto Mercury. To the adaptive optics, it just looked like a really symmetric dark sunspot, and had to hand guide that across the solar surface. The process worked surprisingly well until it got to the limb. Our data processing, the spectral reconstruction, has a real problem when you get to high contrast things like a solar limb. It doesn't know how to deal with that. So here is the movie from the cloud went through from the Mercury transit in 2019. And going across, and you can see all the different solar. And then the system kind of, the processing does not work well at the Finally, here's an example of a nice paper that was published in Science, showing what the type of science that can be done with this telescope and the importance of collaborations. Here, this group took GST BBSO data from the photosphere, showing these bright magnetic features of the photosphere, showed how those traced up into the chromosphere with off-axis or offline H-health images, and also how that corresponded to magnetic magnetograms taken here at BBSO, and finally comparing that to Solar Dynamics Observatory, a spaceborne solar telescope, looking at the corona in the ultraviolet to show that coronal brightening corresponds to these features that are traced all the way back to and below the solar surface. So a very nice paper that was done. And this is something that could not be done with either of these telescopes independently, but shows the power when you have multispectral and collaborations. Here we have the same data product, just visualized differently, magnetogram. Here's the photosphere up into the chromosphere and mapping on up into the corona. So again, a nice paper done. And then lastly, I'd like to finish with this image. It's not one of the greatest images taken, but it actually shows the scene was fairly poor, drops off. So it does somewhat show the how the adaptive optics is correction drops off, going off of the corrected point. But it's just I call this the bumblebee. I like it because it's pretty and it's one that I took. So thank you very much. And if there's any time left, I'm happy to answer your questions.
Okay, let me unmute everybody. Hang on. Okay.
I have a question. I mean, after the pandemic nonsense is over, are they going to have tours for the public still?
The plan certainly was, and last I talked to them, that plan has not changed. That once they are able to fully open again, and everything is open, that they will go back to offering public tours. There is a slight complication in that the tours To handle the tours, the observatory partnered with the Big Bear Valley Astronomical Society. They recently lost their president and vice president, but they are reorganizing, and once they will be contacted by Erica Noro, the admin assistant, and try to get that going again once everybody is comfortable and reopened. So yes.
Okay.
And one thing, if you're ever on that tour, be sure to ask for. Remember, I talked about that plate that is designed to slide into the beam if there's ever a problem with pointing, and that there had been an incident where that plate that did happen, and the plate had a burn through. That plate has now been mounted by the mechanical guy there, Jeff Menow, and is available for display. If you're there, make sure they show you the heat stop, what's sometimes called the slammer, the sacrificial plate. It is quite impressive.
Thank you. Gary, are you there?
Yes.
Do you record this? My power's out up here in the mountains, and I took me a while to get my generator working. So, but I listen to it.
Yeah, what we're gonna do, after I stop recording, it will send me in about 10 minutes. It sends me a link, and I will send it to Claire, who will then email everyone on how to get, how you can view it.
Okay, thank you.
Were you going to put yours? You said something about putting that on your Facebook page. If so, maybe I'd link my own page to that as well.
Yes, yes. Yeah, we'll put that link on Facebook.
Okay, if you would send me that link as well, if you would.
Yes, no problem. Do we have your, Ron has your email, right?
I've been getting emails, so somebody has my emails.
Yeah.
Sends to me, then I'll send to you, and we will get that to you
Okay.
by tomorrow sometime.
Not here. I guess I can put that. Can I figure out how to put that in? Here, I'm putting up my email address right now. So if people had questions or.
Now you got your paychecks from New Jersey, huh?
That's correct. Yeah, for the longest time, I apparently worked for Chris Christie, which in my tenure at BBSO, I actually only went to campus once, and that was to attend the meeting, mostly just to find out what the Center for Solar Terrestrial Research looked like. So I had intended to make more trips out there, but things got busy at work, and then this pandemic thing hit, and which ended up also delaying my retirement. We couldn't hire somebody for me to train to operate the telescope, et cetera. So I was delayed an extra 4 months in my retirement.
Okay.
I have a question,
Go ahead.
Gary.
Yeah.
Can you tell me, Claude, if any of these images are available online? Can you look up what today's sun looks like?
There are the current daily observations are not automatically put up online. There is a gallery page at the BBSO webpage. Let's see if I share screen again. Oh, not there.
It's bbso.njit.edu.
Yeah, or BBSO web, bbso.njit.edu. And there is a gallery page that does have some of the greatest hits images, a few of the things I showed. But to actually get the science data, one needs to fill out a data request form. Most of the data that are taken with the instrument have a proprietary period for the principal investigator that lasts, I think it's 6 months before then becoming publicly available. The photospheric images I showed, those movies, that is automatically publicly available, public data immediately, as well as the H-alpha line centers. The off-line center H-alpha and other data products have that proprietary period in there.
Thank you.
I have a question. Do you have a alert system for the government if there's a solar flare coming?
There is something called the BBSO Solar Forecast Alert. John Varsic is the primary person at Big Bear who writes the daily solar forecast. It was originally intended mostly for the operators to try to determine what would be the best targets to observe for that day. But since then, it has been distributed ever more widely. It is put up every day on the BBSO webpage under one of, I think you go to data, and I'd have to look again where it is exactly.
Okay.
That is done every day. If activity is thought to be high with a high likelihood of a flare, there is an email list that is sent out for solar activity alerts. Anybody can get on that list. You just need to write to John Varsic at BBSO. If you just contact BBSO, and it can be forwarded on to John, or email me, and I could give you his link to request to be put on the activity alert emails. I talked to him just a couple days ago, and he had just changed the software for it, and somehow the alert wasn't working, but I expect he's gotten that working by now. Any other questions?
Big Bears are known a little more for tourism and water sports than for solar observing. Does the town have a lot of interaction with the observatory, or is it like two different worlds?
I would say that there's a lot of misconceptions and misunderstanding about what the observatory is about with a lot of people. But a lot of people have grown up and have had cabins in the area for generations, and are very proud to have a world-class observatory in their backyard like that. And of course, there is, or at least was before COVID, a very active astronomy club in the Big Bear Valley. Did I mention that they just lost their president?
Finally.
7 years.
Are you a Republican president or a Democrat president?
I think we refrain from commenting on that.
I think she was an intergalactic president.
Yeah, there you go.
But yes, the club did a lot of outreach in the area and has a close relationship with the observatory. I was vice president of the club. John Varsic is also a PhD astronomer on the staff there. He is also heavily involved in the club. And a lot of outreach has been done. Monthly, we had a sidewalk astronomy night, which we had branded as Urban Assault Astronomy, where we set up downtown just to show tourists the moon and planets. We would have a dark sky observing night for the star party for the club. I ran a virtual lecture series where we had astronomers from around the world talk to us. This was before
COVID.
Yeah, before Zoom meetings were cool. For many years. We had several other activities. We were very proud of that club, and it was somewhat painful to leave that behind, but I'm sure we will be meeting up with more in the Tehachapi area here.
Yeah, there is one. I had a ranch up there. I just sold it, but there is a astronomy club up there in Tehachapi.
I
I'm trying
have
to
not been
think.
able to find that they are active, so but I've heard rumor that there's, at least we're in Bear Valley Springs, and I hear there's a few guys that will bring out telescopes during eclipses and things.
Mhm.
And I have not gotten any names or contacts yet.
Well, if I can find it, I'll email it to you.
I would appreciate that.
Sure.
By the way, did anybody, speaking of eclipses, did anybody catch the lunar eclipse, or were you clouded out down there?
I saw it in the
Clouded out.
Sacramento area.
Yeah, I was clouded out up at Baldy.
Okay, a couple of us were trying to do a simultaneous observations with a long baseline between Tehachapi and Tucson to do a 3D movie of the,
Cool.
and unfortunately, I had Cirrus, I got some frames, but Matt Penn down in Tucson, apparently he was completely clouded out. This was meant to be sort of a forerunner of another public outreach experiment for the 2024 eclipse. Anything else? If not, maybe I should let you get back to your evenings.
Well, thank you.
Thank you. Yeah.
Well, thank you so much for having me. And like I said, if you'd like to hear anything else, I would love to come back and speak about adaptive optics or something sometime, one of my favorite topics. So have a good evening and thank you so much.
Thanks.
Thank you both.
Thank you.
Good night.
Bye now. All right, we're gonna sign off here. Let me stop. Here we go.